speaking about this. First, Dr. Shankar. He's a research scientist with University of Luxembourg and an expert on the field. He's been working on that for 10 years now. And then we have Dr. Joel Gross. You have met him before. He's from SES. So he will come hopefully in about after 3 and give you a bit the industrial perspective. Now, a few more things. I talked a bit with the program director. We realized that you don't have access to the syllabus, not only for this course, but for other courses. So now all the syllabi should be on Moodle, so you can access it. It doesn't have anything new, but it has all the information that I mentioned in the beginning. I mean, you were asking, what are the objectives of this course? What is the background and so on? So of course I mentioned it in my introductory slide, but now you have it, and not only for this course, but for all the courses that provided such syllabus, it should be on the Moodle. Next point, of course, we discussed also your feedback, you know, that you feel a bit overwhelmed as you expressed also here about the material. So what we can do this year is we try to simplify as much as possible. So we are reducing the material, we keep the most important things. And of course, please don't be stressed about, you know, the marks and all that. As I explained, it's more about the learning. We don't plan to fail anyone. Try to get as much as you can out of this. And of course, we discussed that maybe next year, since, I mean, if we're going to receive similar, let's say, range of background, we might try to split this in 2 semesters, 3 and 3 CTS. So for the people that don't have a telecommunications background, they can take like an introductory course. And then when you come to this, you'll be, let's say, more able to follow through. And of course, that will be available also next year. So if you feel that you have some gaps and you want to fill them in, and of course you have the time because you have other things to do as well and other modules, you are feel free to take this introductory course as well. Last but not least, if you have any other kind of feedback, please don't hesitate to drop me an email. And of course, be a bit sensitive and kind to the people that do the labs. If you have feedback, they're just doing their jobs. Don't yell at them, don't scream at them. It's it's a learning process for everyone.
We've always been, all of us have been on that side, and now we've come this side. So we know what we do when we are on that side.
Exactly. So yes, of course, it's good to have feedback, but try to drop me an email, you can also give it to the people doing the lab, but let's say in a nice manner. So that's about it. I don't want to take time from the lecture because there is a lot of material. So then I will hand it over to Bhavani. Just give me a second to click the button so we are recording.
Thanks, Simos. So I guess you guys are still here after Simos saying that there is nobody's going to fail you. I thought everybody would just leave. Yeah. Well, anyway, good afternoon.
Yes, it's running.
Okay, so what we're going to talk about is on communication payloads, one of the most important things in a satellite. And then what I would say is that this is a real piece of engineering. So people actually build these payloads. It's made up of all kinds of metals and then electronic components. So what I try to give you is a bit of overview of what is the function, what are the key components, what are the key functionalities, and then Joel might be able to shed a bit more insight onto more from an industrial perspective. So of course there's a lot of microwave engineering involved, so I've tried to simplify it a lot. If you have any questions, please feel free to ask. It's not guaranteed that I know all the answers, but I will get back to you with the answers as soon as possible. Before we start, we just have to put some acknowledgements. A lot of this material was taken from a presentation from a colleague, Glenn Thomas from Airbus, who gave a presentation here on satellite payloads. And of course, colleagues from SES, European Space Agency, and our own colleagues from SNT who helped us shape the lecture. We've been, I don't know if the things have been uploaded on Moodle. We made some few changes because we had to reschedule a few things because of our Joel had to have something important. So what I do is right now I would start off with the payload, the functionalities and components, what does the payload do and how is it getting it done. And then, of course, nothing comes with, nothing is ideal. There are always impairments in the payload. So what are the impairments, what are the imperfections, and how is it going to affect whatever we plan to do in the payload. And then Joel will discuss a bit more from a design principle. So how do you design a payload? You look at the services, and then you look at the requirements, and then how you design the payload. And then there is something new that's coming up, which are called process payloads. That's also Joel is going to do it later in the afternoon. Quickly, I am the lecturer for the first half. I've been working here for about 10 years, managing many of the European Space Agency projects, and I have an interest in these topics. So nowhere is mentioned microwave engineering, so the payload is mostly about microwaves. So that's also my first try. Okay, payload. Also, I would say, put a caveat here that I've taken some pictures from the internet. These are all, we don't have any copyrights of any of these, so I have to mention this copyright statement. Okay, so there are two things in a satellite. One is the structure, which is called the bus or the platform, and the other that the kind of whatever goes inside is that which performs the necessary functions. The payload is the term that is used to define whatever that is the set of all the components that performs the necessary function for the satellite. Now, a satellite can be used for different things. It can be used for Earth observation. It can be used by the military. It can be used for the communications here. So, or it can be used for deep space probing. Depending on what is the objective of your satellite, what they call the mission of the satellite, the payload, the platform, everything changes. So that's the beauty of the whole thing. So there's no one payload that fits everything. There's no one platform that fits everything. So you have to look at what are your criterion for design and then design the payload accordingly. Well, there are a few things which are common across all of them. So what I do is to tell you what are the common things across different payloads or different communication payloads. And Joel will try to tell you how a mission or what the satellite intends to do affects the payload design.
So what is now the payload and what is the bus? The bus is everything what is not
I will not say the bus, I would say the platform. The platform is the structure that houses all these components because, I will probably put a next slide here. So if you look at it, you have a lot of things in the satellite. So one is the propulsion. So you want to keep the satellite in the position you want. So you want to move it around. So you need thrusters and then you need fuel tanks and everything. So that's propulsion. Then you need to control the satellite. You want the satellite to do something, you want to maneuver the satellite, you want to increase the power of the satellite. You have to do a few things for the satellite. That's called telemetry. So that's not the user side of communication. It's something private that the operator runs for the satellite. He wants the satellite to increase the power. It's a nice way to increase the power. He wants to move the satellite. So all those things are telemetry and command. Telemetry and command. That's one thing. Where do I get power from the satellite? I need to generate from the solar panel. So we have each of them separate components, and all these components are housed together. The structure that houses together is the platform, is the entire thing. And then payload is one part of it where it performs the desired objectives of the satellite mission. For example, if it's a communication satellite, it tries to connect point A to point B. It does everything that is needed to connect point A to point B. And all the other things are within the platform.
So the payload in this case would be an antenna and a communication system.
Yes.
But if we have a observation satellite that is only taking pictures of the Earth,
so it has to take the pictures.
Then
so the cameras, everything, they form the. Well, of course, it takes the picture and it has to put it back to the ground. Mm-hmm. So that whole link, it's taking the pictures, putting it back to the ground. So it takes the pictures, does some processing, it compresses it or something, and then it has to pass it through an antenna and put it down to the ground.
But the antenna used for moving and maneuvering the satellite is not part of the payload then?
The antenna is part of the payload.
So also the antenna for commanding?
The antenna usually, okay, so, well, there is only one antenna. For our purposes, we can take there's only one antenna that's shared by command and the communication. But these are running on different frequencies, so they don't interfere with one another.
Maybe just to specify also that one satellite can have multiple payloads, right? You can have multiple missions. Each mission might have a certain payload, right? But they might all share a common communication payload, for example, for grabbing all this data and putting it down to Earth. So the payload is essentially a part of hardware that does part of the function, but then depending on the satellite, you might have multiple of those being hosted under the same platform, right?
Exactly. So the platform is a structure, the payload is one part of the, I would say the life of the satellite which does a certain functionality. All these things you could consider the platform as a skeleton, the other things as kind of key internal objects performing different functionalities. Okay, so now to answer your question, what is there in a payload? We are now looking at communication satellites. The communication satellites are those who want to connect point A to point B, the communication between point A and point B. So what does the communication payload have? It has two components. One is the antennas, and then you have something called the repeater. We will come back to that in a minute. So the payload has two things, the antenna subsystems and the repeater. Okay, so here is where the saying that so antenna is part of the payload. Because again, antenna defines where your satellite is looking at, and where your satellite is looking at depends on what was the satellite designed for. So it's part of the mission specific, and then it's a payload design. And right now, in this lecture, we will look at a bit about the repeater. Joel will come back and discuss a bit more about the antennas. So what I'm looking at here is an uplink that is from the ground. You have a big gateway, for example, putting up the signals to the receive antenna. There is some processing happening, and then that is being put out onto the transmit antenna for a user downlink. So we have this kind of this uplink and the downlink here. Okay, so what are the challenges that we would like to see in that you have in a repeater? First thing is, I will just start to say input signal power. So what is the power that we get at the input of the satellite? For example, I'm looking at geo satellites which are 36,000 kilometers above or more than that. You know what happens is that the electromagnetic radiation spreads, and so there is as and when you move further away from the source, the power goes down by R squared. So for some frequencies of operation, you would lose about 200 dB. So that means if I were to transmit some power like 10 power 8 watts, 10 power 8 watts is 100 megawatts of power. If you transmit 100 megawatts of power, you would receive 10 power minus 12 watt at the input of the satellite. So it's not even microwatts, it's much lower than that. It's very much lower than something nanowatt, even less than that. So you are operating a system that is supposed to take this, and again, you have to put it back to the ground where it has to still face 200 dB of power loss. So at the end, if you don't do anything on board, then probably you get garbage. So you need something that tries to take this and try to make it something meaningful. So the first thing that it has to do is to do some kind of amplification to make this power meaningful.
So the antenna is passive antenna.
Right now, for this part of the lecture, it's passive. So maybe in the novel payloads, maybe we discuss a bit about the active antennas that the other, yeah.
What is the difference between repeater and relay?
One, relay, you will see that the repeater does much more than the relay. So you will see all the when you see the block diagram, you will see how it differs from the relay. But in essence, it's more or less the same thing, but it's kind of an advanced relay. Well, the other thing is, this is one difference between a relay and a repeater. Whatever you want to transmit uplink, the frequencies that you're transmitting here is not the frequencies that you are allowed to downlink. Yeah. So it's a uplink and downlink are in what they call frequency division duplex mode. So you transmit in one, you receive in the other. So this is by regulation. There are a few other things to it. So I cannot just take something that comes to me. I have a fancy amplifier that makes this meaningful and just dumps it down. No, I cannot do it because I need to do a frequency conversion. So amplification, frequency conversion. And the third thing is that a satellite has a wide band of operation. Usually 500 megahertz, 2 gigahertz, a lot of bandwidth there. And then, so what usually happens is that not everybody requires so much. So what the satellite operator does is he splits this bandwidth into small chunks. And then these small pieces of frequencies, for example, here this needs to go to Scandinavia. It's just a local broadcast to Scandinavian countries. I couldn't think of anything, so I just put up some names here. But then, well, for example, county cricket in England, probably only those people in the British Isles want to watch it, not many. So you have few things which are quite local, and there are a few things that are global. Everybody wants to watch football. So what happens is that the signals are multiplexed in frequencies, different channels, for example, a bouquet of channels, Sky TV and other things, they're all multiplexed in these frequencies. And then all of them have to go to different beams, to go to different parts of the satellite system. So you cannot, even though if you amplify and you down convert, you still need to separate the signals on the satellite and so that they go into the right beams. So another important thing is you need to switch or you need to route on the satellite. So you get something up, and then it's kind of all pre-decided that this goes here, this goes there, but it still has to be implemented on the satellite. So that's how it differs from a relay, because the relay would probably amplify it forward. It just amplifies and puts it up. Here, it is not the case. It does three different things. It amplifies, it down converts. I'm looking at the direction where you go from a big gateway to a user. And then it has to switch and route. So these are the three things that a payload has to do, or the repeater has to do. So now let's look at the big picture of how the repeater does it by this. So we have the uplink antenna system. That's the first, I would say, first component that tries to help you with the signal power. It is a huge dish, so it gives you a certain amount of gain. We will see that in the lecture afterwards. And then you have something called a rejection filter. It tries to throw out some things that are not needed. We'll also discuss this. All these things I will discuss in the other thing. Then you have a low noise amplifier, a frequency conversion. So you do it progressively. Try to get rid of some unwanted things. Try to make the signal a bit more meaningful. Try to go down on the frequency conversion. And then is the main component, which is called the transponder, which does the high power amplification. I will tell you how much is the high power amplification when it comes to that. It takes, for example, microwatts to watts. So microwatts is 10 power minus 6. 10 power minus 6 to 1. So that's the kind of gains that, the amplification gains that is being done here on this high power amplifier. And then it goes out onto the downlink. So this is what a repeater, if you include the antenna as a payload, would look like. Okay? So our aim right now is to look at each of these components a bit more in detail, try to understand what each of them does and how is it being done. Feel free to stop anytime. Just to drive home the fact that you need some amount of power amplification, this is just to recapitulate. So you have done EIRPs already?
Yeah, they've done it with
okay.
Before, yeah.
So effective isotopic radiated power 80 dB watt is about 100 megawatt. It's not 100 megawatt of power that you're transmitting, because 100 megawatt of power you would need a nuclear station next to your antenna. No, what you're transmitting is say 100 watt or something, 200 watt of RF power. But you see the antennas, they're quite big, 10 meters. I've probably been to SCA that you've seen. So that 10-meter antenna gives you 50, 60 dB of power gain. So instead of I would say this, instead of the electromagnetic radiation spreading out in all directions, it focuses into a certain direction. And this amount is, the amount by which it kind of focuses is about 50, 60 dB. So when I say effective isotopic radiated power, it's not the power that is fed into the antenna, but it's the effective power that is put in a certain direction, which includes the antenna gain. So if I have 80 dB of power, And then, the power flux density goes on with like this, and then when you receive, you would receive a power flux density. Power flux density is just the power divided by the area, because even if you focus it, there's a radiation that's happening, and so this is the surface area of a sphere. So the power plus unit area goes down. This is the reflect power that you get on the satellite. Now, there is one possibility that if I have a very big antenna, so this is, if you look at it, this is basic physics, dimension matching, watts per meter square. So if I want to have watts, I would just to multiply by meter square. That meter square means the area. So if I have an amazing area, a big antenna, then I would put a very big antenna, so that kind of multiplied by area, this should go up. But, yeah?
Why does receive power is negative?
It's in dB, and decibels. It's 10 power minus 8. It's in decibels.
It's very, very small.
Very small.
It's not negative, but it's very, very small.
It's 10 power minus. But then on the satellite, well, we don't have much space. So the area of a satellite is 0.1 meter square, like 10 centimeter by 10 centimeter, or 20 by 20, or 50 by. That's the maximum you can put an antenna on board the satellite. So you would get the received power is 1 nanowatt. This is what you get on board the satellite. No. This is without the antenna. Okay. But then, if it was only power, you could have done something. But then there's always our friend, the noise. So you have noise everywhere. You have the device noise. You have the background noise, because Earth also radiates microwaves from all frequencies. So you have unwanted radiation from the Earth, and that's called the Earth brightness temperature. So when all this noise, everything is characterized by an equivalent black body whose temperature is given by here. All these things are in Kelvin, 4 Kelvin, 310 Kelvin. So it tries to tell hotter the black body, more is the radiation, more is the noise power. So this is what is done in. So the noise power, there is a standard formula to calculate. If you don't want it, it's fine. But then you just have an idea of it. The good thing here is that unless you have pretty bad situations, or where you have very bad noise injection into the system, your noise power is also very low. It's minus 110 dB watts, quite low. So the signal to noise ratio that I'm talking about, for example, my signal was minus 92 dB watt, and then my noise is minus 113. The signal to noise ratio is signal power by noise power, but when I do log the dBs, it becomes a difference. So I take out minus 92 from 113. So you have about still good signal to noise ratio of 21 dB. That's a very good signal to noise ratio. Well, these are cooked up example, but usually it varies between 15 to 20, something like this. But, well, SNR is not the only thing. If you don't even have a good signal in the end, you should be able to receive that signal on a device, and then that should be made meaningful. Okay, so SNR itself does not say you anything, but what it means here is that this is the SNR that you have at the input of the satellite. And only that all that you could do any further is to degrade it. Because everything else that comes after increases the signal, and it also increases the noise. And then it might even add more noise, because you're not adding any more signal. The signal has already come in. All that you would do is add more noise. So this sets the limit for how much you could do for the user. So it's very important that you try to design a system. When you design a system, you look at the uplink from the satellite, from the ground to the satellite, and try to make that SNR quite high, so that even if you inject a bit more noise through components, through other things, you're still able to get a good SNR with the receiver on the ground. Okay? Okay, so that's the thing. Now we start looking a bit more into the rejection filter. What does it do? So, for example, on the frequency, you have your desired signal in green, but then you have only certain bandwidth in which you can transmit. But you have no control over noise. Noise can be wideband. It can be anywhere throughout the whole spectrum. And of course, there will be people who are given some other frequency bands to transmit, or somebody wants to do a malicious transmission. So then you have interference. All these things are getting into your system. The antenna, well, it has some frequency response, but for the time being, assume that antenna just lets it whatever comes in, it puts again and puts it through the system. So what happens here? So all these things get added up in time. So for example, if this was the frequency, then I wanted a sine wave, and then this is what happens. There is a sine wave, but then that's modulated by another sine wave. I don't know if you could see this is lower thing, and then there is noise on top of it. Now, what the rejection filter does is it tries to match, put a filter which tries to take only what is desired. Of course, whatever noise is there, whatever interference is there within that band, it cannot reject. It takes everything in. And so, what happens here, it tries to take the desired signal, and it reduces the bandwidth of the noise, because the filter would be something like this, so some parts of the noise will be cut off. When you cut off noise, that means that you are taking out some power of the noise. And so
the rejection filter, is it a notch filter?
No, notch filter is one which eliminates only one part of the frequency. So here what we do is a band pass filter. You pass a certain band. Notch is an inverse of just put. If you don't want something, a particular thing, you put a notch. Here you do the other way. You want this to pass, so you pass it and then you drop the other things. So in the end, it would look something like this. You're getting a sine wave that you want. More or less, of course, there's some noise, but you assume something else will take care of it. So this is what the first the rejection filter does. Well, people call it with different things, call it pre-select filter, different things. So it does two things. One, it eliminates out-of-band interference, it eliminates out-of-band noise, and then it reduces the corruption of the signal. Okay? There's one more thing that also you should take care of, is that sometimes you have for example, there was no noise, there was this, and you had this interference very high, and you let the system inside. Of course, it is corrupting the signal, but what would happen is that this power level is so high that whatever comes afterwards, it does not see any changes because of this. This power level, for example, is 100, and then this power level is in the range of 1 or 2 watts. Then on 100, you don't see much change with 1 or 2 states. So this is what they call saturation of the amplifier. So this also happens on the subsequent things. So you want whatever here to be reflection of your signal. But if you don't see that happening, then you say that your receiver is saturated, and no matter what you do, you're not going to get anything. So the rejection filter tries to get rid of this saturation and also eliminate out-of-band noise, so it's a more meaningful thing. Okay.
The saturation is caused by the interference, is that what you know?
Well, the saturation is caused by unwanted interference. That gets in, it's in time domain, so they add up, and then I would say that the amplitude of that interference is quite high.
So the power of the interfering signal is more than the real signal.
Yes, and then what you see is the variations you see is because of the interference and not because of the signal. So then no matter what you do, what you process, you're processing the interference and not the signal.
In the previous slide, when you said the signal corruption, does that refer to interference and noise together?
Yes, everything. Because in frequency you see separate, but what you see is in time domain. Everything is working in time. So this is what you see. You have interference and noise. And then it takes out the interference, and then you see a cleaner signal. Okay. Okay, so now we have the antenna, we try to remove a bit of the signal, unwanted systems. Now we assume that we have our signal of interest, And then we have to make it a bit more meaningful for the satellite itself, for the further amplification stages. So you cannot take 10 power minus 9 watts to 1 watt in one stage. That doesn't happen. So you have to do it multiple stages. The first stage is called the low noise amplifier. The low noise amplifier is the first active, I would say, it is the first component. It amplifies signals of some low strength. The problem is that whenever you have this is a solid state, you have a chip, for example, or a component, everything adds noise. So if you add noise at the very beginning, so you had noise that was coming from the environment, and then okay, there's noise coming in, and this is the first time I'm kind of, well, this also has a bit of noise that's neglected, but here, if I add more noise here, then that noise gets into the system. So this is the first component. So you want this guy to have as low noise as possible, as low noise as possible. You should understand that whenever you put anything, it adds noise. So well, any active component, it adds noise. Because the electrons and then they keep jumping randomly, so it adds noise. Any active component adds noise. So you want to have a very low noise, as low noise as possible to be included here. So the problem is that if you want to make that happen, you don't get much gain. So you cannot have a free, it's like a no free lunch. So what happens is that you can get about 50 dB gain. This is what I would say. So from 10 power minus 9 watts or 10 power minus 5, 10 power minus 1, you go to 10 power minus, I would say 10 power minus 5, 10 power minus 4. So you're still in the milli, micro watt region. So the first is the electronic amplifier, and then this also is a multi-stage amplifier. The first stage is the lowest noise, and then everybody adds noise, and the highest, the last stage, sorry, it's not the highest stage, it's the highest gain amplifier that comes in. It's the first low noise amplifier that comes in. And then you should also keep an idea that the temperature here means how much noise it adds. Okay? Higher the temperature, higher is the noise. And the way we relate the temperature to the noise power is through the formula KTB. K is the Boltzmann's constant, T is the temperature, B is the bandwidth. And then this is how it looks like in a component scale, and it's about half a kilo. So this is the first thing. So another thing what happens is that, as I said, you should try to keep you should keep the amplifier cool, because if you make it hot, the temperature increases, so it starts putting out more noise than needed. And then at the same time, you want to put it very close to the antenna, because the antenna to the amplifier, there is a piece of metal pipe which they call the waveguide. It's a metal pipe. There's no wires. It's all high frequency microwave. So you have a coaxial cable, kind of what we have now, or typically a metal thing. And then when you have any radiation passing through the metal, you know what happens. Sorry?
Electrons are
No, the metal heats up. So it absorbs power. So there is an insertion loss. So if the longer the metal, the poorer is it absorbs more. So the signal power when you at the other end is quite small. It's lower than what you had at the beginning. So you want this to be small. So you try to put the LNA close to the antenna, and also you want to try to keep it cool. So there are some devices that try to keep the system noise temperature low. Okay. Good. So we did some sort of low noise amplification, and then comes the frequency plans. As I said, the uplink and the downlink are on different frequencies. Here is an example that I took from this paper. There are 4 links. If you look at from a satellite, you have a gateway, you have a user, you have a satellite. So uplink, you have gateway to satellite, user to satellite, both uplinks, and then satellite to user, satellite to gateway, downlinks. 2 uplinks, 2 downlinks. Okay, and typically the uplink and the downlink are frequency separated. So, for example, I don't know, you see here, You could see from here the uplinks and the downlinks are in different shades. So you could see that this is the uplink, or this is the downlink, this is the uplink. They are in different shades. Well, it's too small to see, but then if you realize, if you have a good eye, then you will always see that the uplink has a higher frequency than the downlink. It's not obvious, maybe if you can, but it's always higher than the downlink. That's why we call it a down conversion. The uplink is at the higher frequencies, and then you have to bring it down. I will leave it to you to think why this is the case. Why is the uplink always more than the downlink? And why do we call it an up conversion, down conversion, and not a down conversion? If you could think about it in your spare time. Okay, so
the gateway size, like we can use the higher frequency because it's about the power, right? The power is linked to the frequency.
yeah, I mean, but higher frequency means higher losses because that propagation loss is much higher for higher frequencies.
Yeah, but then we are uplinking, so we can make up for that loss with our gateway.
So something like that. So you try to see where you could position, where you could have, for example, I cannot have a user with a big antenna. I want to have a user with a small antenna. So even if it transmits with a smaller antenna, maybe on a satellite I could have a slightly bigger antenna than the user. So that compensates for, so that's why you would put a higher uplink. So it's basically that in smaller system design problem where you try to exploit the fact that higher antennas can be put on some locations and be used. Okay.
You mean that if it is possible to have the same uplink and downlink, the power of uplink and downlink would be equal?
No, power of uplink and downlink, no, I'm not saying that, no. Now what I'm going to say is that if I were to transmit the same power from uplink or on uplink and downlink, when you receive for the same distance, the uplink has a lower, value. You receive much lower power on the uplink than on the downlink. Because the frequencies are different, the downlink has a lower frequency, so it needs to travel much farther to have the same attenuation as the uplink. For example, I would say that if the downlink frequency is half the uplink frequency, is half the uplink frequency, this is an example, then the attenuation is 1/4. So the loss is 1/4. Okay, so it doesn't lose much on the downlink. So for example, on the downlink, if I have a big satellite antenna and a small user antenna, it works. Okay, so let's look at the down conversion. That's why it's called a down conversion. Let's look at the down conversion principle. What happens is that I have a signal at some frequency f0. And then you have a local oscillator. When you have a source or a sinusoidal source, something that tries to bring to whatever you want. And then what you do is you have this, which is of this form, and then you somehow multiply. Let's, for the time being, not worry how this is done in practice. What is a component that does it? So mathematically assume that I have this signal, I have a cos, I multiply this, and then if you know from your Fourier theory, then it splits. You will get both a signal at f0 plus fc and f0 minus fc. So you will get two components. And if you choose carefully your fc, then this, if for example, now we look at this, f0 minus fc will have a much lower frequency than f0. It is sort of already down converted. This guy has a much higher frequency than this. So if you can get rid of this component, you are already, you put a filter which removes that, and then you're already in down converted mode. So choosing your fc properly depending on f0, you will be able to go down on the frequency. So this is a very simple thing that is being done in sampling. Or anything. Mathematically very simple, but a few things that we need to
This
understand.
question, how many people have done Fourier transforms. Because not even that is not okay. Good. If you haven't done it, just take it as given. You know that if you multiply the two frequencies, you get this as an output.
Okay. I was thinking. I'm thinking if I can get. I'm thinking of something practical. Tune the radio, something happened. But if I get, I'll let you know. Okay. So the three things that we have to worry about here. How do I generate this? I need to generate a good reference signal. It should not be that, oh, it's giving me this frequency. Now after some time it is gone somewhere else. It's like a mechanical clock. You know, you wind for some days it's working and then it starts losing time or gaining time. So maybe this guy could lose frequencies or gain frequencies, then this changes. Okay? First thing. The other important thing, I put a multiplication here. Okay, I can do it on a laptop or computer, but these are physical devices. This is just, well, this is probably an oscillator, a crystal, and then you have a pipe coming, a metallic pipe, or other metallic pipes. How do I even multiply? So that's called, that you have to understand, it's called a mixer. And then I need to have a good filter to get rid of this. So these are the three important things that we need to have for a good down conversion here. So what this is, I'm not going into the details. So the whole thing is implemented in a circuit like this. Don't worry about it. And then it comes in a packaging like this. So it's simple, but then you understand the principle that there is, okay, another filter here, but you can neglect it for the time being. And then you have an oscillator which multiplies, and the multiplication is done in a thing called mixer. Don't worry about it, but it's a nonlinear device that does the waveform multiplication. Okay, here is the thing. Well, everything, as I said, is devices. That is, well, in this part of the lecture, everything is device. So then people realize that probably it's difficult to have everything on using analog components. So then they try to make it more computerized, and that's why you have the novel payloads that we're going to look at the end of the lecture. So these are devices. Well, I don't know if this is a bit involved, so I will not go into details. But there are architectures, there are devices like diodes or transistors and transformers that let you do what you want to do, which is the mixing, which is the waveform multiplication. The other important thing is the oscillator. The oscillator is the kind of the clock, as people talk about. You have this piezoelectric effect. You give a bit of voltage to a crystal oscillator and it starts oscillating, and then you can measure the frequencies. These are typically used. Of course, you cannot just put anything there. There are aging effects. After some time, it's not going to oscillate at the same frequency as it was earlier. And another important thing, I don't know if it has been told, the satellite sees sun for quite some time and then it's cold for quite some time. So when it sees the sun, everything heats up. And in microwaves, and everything heats up, the characteristics change. So they are called the diurnal changes. So in mornings you will have a different filter, in the evenings you will have a slightly different filter. So that as everything changes with temperature, so does the crystal oscillator frequency. So you need to put a decent amount of temperature compensated cabin or compensation there. On the other hand, you could also look at, I don't know if you recall from your high school physics, you put a capacitance, for those who have done physics, you put a capacitance, you put an inductance, and then you would get a resonance circuit. So people who have also tried, these are more electronic oscillators, these are not crystals, but these are more devices, chips that you could also use for generating the oscillations.
Sorry, are we using a mixer to tuning the frequency in the signal channel?
The mixer does you could also call it. Yeah, well, it depends on what the mixer includes and what the mixer does not include. Right now I said it's just a multiplication. Okay, so it just multiplies. So you tune by tuning the oscillator. Okay, I mean, that's how. But you want to think about it as the whole block, the multiplication with the oscillator as a mixer. Yes, then it is used to tune the frequencies you want. It's just a notation how you. Okay, so we have probably a few minutes. I will close this, and then can we take a break now, or it's 45 minutes?
It's up to you. If we're waiting for Joel, we can finish this up and then have a bigger break till Joel comes by.
Oh no, I have some more.
You have some more? So we can have a break now then.
Yeah, I would. Yeah, then we can come back and then focus a bit more on the others. Another 15-20 minutes.
Okay.
Okay. If you call this whole thing, then I just tune this and this. But if I just call this mixer, it's also that's all. You have the point if you tune an oscillator that changes, and of course you also have to keep the right filter. So when you tune a different frequency, these things change here, these things go in different frequencies. And so the filter has to throw out the right one. So you have to tune this.
You know what I mean? So, to me, that's and
I was doing speech, so I need to do it now.
You just can't show. You want to see the result, or can just hear the result?
I just noticed the execution part is always generating new values. So when you put constant, change all the time.
Yeah, because it's keep running. You can just.
Oh, it upload. Yes. Just the begin the course and it didn't change, and now it's changed. Yeah.
Because we try to make it run.
Guys, sorry. So just to let you know that you have the class of space resources in the lesson 5 o'clock. So we can meet in the basement, so the section. Okay?
Utsav, for example, wants to identify more information. So can he have the next link is possible? The post services.
So what you do is the best thing we can do with this. That's why we talk to Tony, so we can get communications. People can easily follow it.
Example.